In this segment, we look at search trees, which are a particular kind of binary tree designed to give us efficient information storage and retrieval. So suppose we're storing collections of integers. I mean, the obvious first choice would be to put the collection numbers in a list. Now, would you say was the average time taken to check whether something is a member of the list? In the case of the element 2, we only have to look at the first element of the list. In the case of the element 4, we have to look 3 out of the 4 elements. For the element 3, we have to look at every element because 3 is not there. So it looks like we're going to be linear or something close to linear. And so the longer the list, the longer time it will take us in a linear scale up, the longer time it will take us in general to check whether something's a member of the list. We know for things that are not members of the list, we will have to check the equality of the item we're looking for against every item in the list. Now we can speed that up a tiny bit in the case of ordering a list. We can, for example, if we're looking for the element 3 in a list, we know once we have got past the number 2 in the list, if the subsequent number is not 3, then we know that we have reached the point where 3 would occur, and if it doesn't occur, it means 3 is not a member of the list. So it allows us to conclude that something is not a member without examining the whole list. Whereas in the unordered case, we had to examine the whole list. We couldn't predict in advance where 3 would occur if it occurred at all. So this gives us some sort of speed up, but in fact, it's still linear. So what can we do that's substantially better? The answer is we can build what's called a search tree. We store the numbers as nodes, the values held at nodes in a tree, and that tree is one that has a special property. The property, which we call an invariant, is that the tree is ordered. And by that I mean, at the top node, if you look in the tree, the left subtree, every element in the left subtree is less than or equal the element at the top. And every element in the right subtree is greater than the element at the top. So we know, for example, if the element at the top is 5 and we're looking for the number 4, we only have to look in the left subtree. If we're looking for the number 10, we only have to look in the right subtree. So we don't have to check everything. And as we go down the tree, you can see that if we're, for example, checking whether 6 is a member of the tree, at the top we have 5, so we have to check the right subtree. That has 7 at the top, so we have to check the left subtree. We find, 6 is here. Similarly, if we're looking for 8, we'd first check the 8 against 5, and then we would go to the right. We'd then check 8 against 7. We go again to the right, and then we would check 8 against 9. It would say go to the left, but then it's an empty tree underneath 9 on both the left and the right. So we conclude, after checking against 3 numbers, we conclude that 8 is not in the list. And you can see in the collection, and you can see here that we are basically needing to use something like the logarithm of the number, log to the base 2, because a binary tree of depth 3 has 2 to the 3 minus 1 nodes. So we get almost 2 to the 3 nodes inside a binary tree of depth 3. So we are, if you like, if the number of nodes is n, then the depth is log to the base 2 of n. So we are getting a more efficient conclusion that either an element is in or it's not by using a search tree. So I've explained informally how lookup behaves. I leave it to you to define that for yourself in an exercise. What I'm defining here is how you insert an element into a search tree. Now, there are two cases. The first is that the tree is empty, in which case we create a new node which has that value x as the value in the node and 2 empty subtrees. If, on the other hand, we have a node which is not empty, so the value held at it is b, then if x is smaller or equal to b, we insert x in the subtree to the left. If it's not, we insert x in the subtree to the right. So you can see this recursion is giving us, it's handling every possible case. And what happens is you either insert in if it's smaller, you insert in the left subtree. If it's larger, you insert in the right. I'll again leave as an exercise for you. Suppose we were maintaining an extra invariant for the tree that it contains no duplicates. How would you handle that? How would you modify this definition? Suppose you had a tree which had no duplicates in it. How would you make sure that when you do an insertion, you don't create any duplicates? So I'll leave that to you to judge.